This aircraft, created behind bars under the watchful eyes of guards, became one of the most survivable and effective bombers of its time, despite incredibly difficult conditions. Friends, meet the Tu-2, a Soviet machine born within the walls of a closed design bureau of the People's Commissariat for Internal Affairs, which proved its worth despite its late mass arrival at the front. How did aircraft designers, serving sentences on fabricated charges, manage to create an aircraft capable of competing with fighters in terms of speed? Why did this bomber carry 3 times the bomb load of the familiar PE-2 and continue its flight even with the completely failed engine? Today we will analyze in detail the history of this unique aircraft's creation and its Tu-2's modification. Be sure to watch this episode to the very end. You will learn how Tupolev's personal letter to Stalin saved the project from cancellation, and how the Tu-2 played a key role in overcoming the powerful defensive lines of Königsberg. Let's begin. A lamp burns behind a window without curtains. On the table lie a pencil, a ruler, and a stack of blueprints covered in small, cramped handwriting. The man at the table raises his head only when footsteps are heard in the corridor, not before. This is no ordinary design bureau. The door here is locked from the outside. The man's name is Andrei Tupolev. By 1938, this name was already known to the country's entire aviation industry. Dozens of built machines, international recognition, and a reputation as one of the leading designers of his time. And then, in a single night, everything changes. He is arrested on charges that, many years later, will be recognized as completely fabricated. The article is political. The sentence is real. It would seem that the designer's career should have ended there. But something occurred that aviation historians still call one of the strangest decisions of its time. Instead of writing off the experienced engineer, they put him back behind the drafting table. Only now, this table was located inside a special regiment institution. Thus emerged what would later be called a special design bureau, a closed structure where specialists continued to work in their profession, but under constant supervision and without the right to leave the territory. Tupolev was allowed to personally select the engineers for his team. He chose them not by their records, but by their capability, seeking those who understood aerodynamics, structural strength, and engine building. Many of them were right here, under the same fabricated charges. A strange and terrifying thing resulted. Under one roof, they gathered some of the country's best aviation engineers and simultaneously deprived them of basic freedom of movement. Working spaces were allocated directly on the territory of the institution. Access was controlled by guards. Every calculation sheet, every sketch was checked, and every movement was recorded. It is difficult to imagine normal engineering work under such conditions. Yet it was precisely here, behind these walls, that one of the best bombers of its generation was to be born. Here is what is worth knowing before we go further. The aircraft we are talking about today would later be called one of the most reliable and versatile combat machines of its time. Pilots would praise it for its responsive handling. Opposing engineers would study captured specimens with undisguised interest. In terms of its characteristics, it would surpass the enemy's best fighter at that moment, and this would be the result of precise engineering calculation, not coincidence. But in 1938, none of this exists yet. There is only a man at a table without the right to step outside, and a task that must be completed at all costs. The strangest part of this story is not even that a talented designer ended up in custody on a false charge. There were many such stories in those years. The strange thing is that the system that deprived him of his freedom simultaneously presented him with a task of national importance and expected a result. Tupolev signed technical documentation for an aircraft whose development rights formally belonged not to him, but to the structure in which he was held. Every drawing passed through the hands of a man whose own status remained uncertain. He was creating the future of Soviet aviation without knowing what future awaited him. The history of the Tu-2 begins precisely here, from a strange, almost impossible combination of talent and confinement. To understand how a machine with such a fate managed to become one of the best in its class, one must first understand how the system in which it was created actually functioned. The workday here begins not by an alarm clock, but by command. A corridor, stairs, another corridor, and only then a door with a sign, behind which design work begins. Steps are counted. The route does not change. The specialists of the Special Design Bureau lived on the territory of the institution where they worked. They slept in one building and drafted in another. A walk in the yard was the event of the day. A letter to relatives was a rare privilege that had to be earned. Yet, strange as it may sound, it was under these conditions that the engineers received something many free design teams of the time lacked: the opportunity to focus exclusively on the task. No external meetings, no bureaucratic routine, no distracting factors from the outside world. Only the drafting table, the assignment, and time, which was catastrophically short. The paradox of this system was that it simultaneously suffocated people and forced them to work to their absolute limits. Tupolev selected the team himself. Among those he chose were specialists in aerodynamics, structural strength, and power plants, people whose names would later become known to the entire industry. Each was responsible for their own sector. One calculated wing loads, another worked on weight distribution, and a third struggled with how to position the crew so the machine remained maneuverable yet protected. A legitimate question arises: how is it even possible to design a combat aircraft in such cramped conditions? The answer is both simple and complex. It was possible only because these people knew their business better than anyone else in the country. They did not need to be taught the basics. They just needed to be given the task and left alone to solve it. But they were also disrupted. Every drawing, before moving further down the chain, passed through the control of guards. This was not a technical check. They verified not the calculations, but political reliability. People with no connection to aviation evaluated papers they understood far less than the authors did. Here is a detail that shows the true scale of the difficulties. Access to reference literature, test data, and information on foreign developments was severely limited. A regular design bureau could request necessary data almost without delay. Here, every such request turned into a separate procedure that took days and sometimes weeks. Engineers had to recall formulas and tables from memory that, under normal conditions, they would have simply taken from a shelf. They solved problems literally from scratch where free institutes had ready-made developments. Yet, despite everything, results appeared. Slower than desired, but they appeared. The daily routine here resembled a military barracks rather than a typical concept of a designer's work. Wake up, roll call, work at the table until late evening, another roll call, lights out. No weekends in the usual sense. No right to say, "I am tired, I will continue tomorrow." And yet, it was in this atmosphere that the aircraft was born, which frontline pilots would later speak of with genuine respect. It is important to understand one thing about the Soviet aviation industry of the late 1930s. The country desperately lacked modern combat machines. Every day of delay meant falling behind rivals who already possessed more advanced technology. This is why the country's leadership took this strange step, isolating experienced specialists physically, but not rejecting their knowledge. Cynical? Absolutely. Effective? In a strange way, yes. Tupolev and his colleagues understood the stakes better than anyone. They knew that the result of their labor would determine not only their own fate, but also the combat capability of the country's aviation. This thought, judging by the memoirs of those who worked alongside the designer, kept the team focused more intensely than any guard at the door. By the end of 1940, the first outlines of the future machine had already landed on the table. This was not yet the aircraft that in a few years would be called one of the best bombers of its class. These were only the contours of an idea, but an idea so thoroughly considered that, even under strict control and a shortage of resources, it began to take shape. And this shape promised to become something special. The first question that faced Tupolev's team sounded deceptively simple. What should a next-generation bomber be like? Deceptively, because behind this question lay a whole knot of contradictions. The machine had to fly as fast as a fighter. It had to carry a substantial bomb load like a heavy bomber. It had to climb to high altitudes beyond the reach of most anti-aircraft defenses of the time. And at the same time, it had to remain simple enough to produce under conditions of material shortages and a lack of skilled labor. Any engineer will tell you that combining all these requirements in one machine is nearly impossible. Every improvement in one direction inevitably compromises another. If you want more speed, you lighten the structure. If you lighten the structure, you lose crew protection. If you strengthen protection, you lose speed. It was a closed loop that dozens of design teams had tried to break, only to fail. Tupolev approached the task unconventionally. Instead of choosing between extremes, his team began searching for an architectural solution that would shift the very boundary of compromise. The key decision was using 2 powerful engines instead of 1. At first glance, an obvious step. In practice, a major engineering challenge. 2 engines meant 2 sources of vibration, 2 sources of potential failure, and doubled complexity of the fuel and oil systems. But they also gave the machine something single-engine counterparts lacked, a margin of safety. If one engine failed, the second could theoretically keep the machine flying to its airfield. This decision, made at the stage of the very first sketches, would later save the lives of dozens of crews, but more on that in a moment. Initially, the designers were tasked with creating a short-range, high-speed bomber. The machine was to operate at relatively short distances, delivering precision strikes and returning quickly to base. However, during the design process, it became clear that the potential of this design was much broader than originally assumed. The engineers working on the fuselage noticed an interesting feature. The volume of the internal bays allowed for significantly more equipment than was required for the basic version. This meant that, theoretically, the machine could be used not only as an attack bomber, but also as a reconnaissance aircraft capable of staying aloft for long periods to gather valuable data. Thus, versatility was built into the project, a quality that would ultimately become one of the main signatures of this aircraft. Here is what is worth understanding about engineering under severe shortages. When you do not have the opportunity to build 10 different specialized machines for 10 different tasks, you are forced to create a single machine capable of performing as many of those tasks as possible simultaneously. Not because it is the ideal engineering solution in theory, but because there are simply no other options. The team also faced purely practical limitations. Available materials at the time, particularly high-quality aluminum, were supplied inconsistently. Designers had to allow for the partial replacement of metal elements with wooden ones without significant loss of structural strength, a decision that many colleagues in the field would have considered an unacceptable compromise. Tupolev thought otherwise. In his conviction, an aircraft that could be built here and now from available materials was far more valuable than a theoretically perfect machine that could not be produced in the required numbers. This philosophy, practicality over perfection, permeated the entire project from the first sketch to the final drawing. By the end of the concept development, a document lay on the designer's table describing a machine that was supposed to be as fast as a fighter, as durable as a heavy bomber, and sufficiently manufacturable to be assembled on limited production capacities. This sounded almost like a list of impossible demands. But the team working behind the locked door specialized in turning the impossible into drawings, and drawings into metal. Only one question remained. Would all of this work in reality when it came to assembling the first prototype machines? The end of 1941, an airfield covered in snow, the rumble of engines in the distance, and several new machines rolled out of the hangar onto the airfield. Externally, nothing special. Just another set of aircraft with factory numbers on their sides. But it is from this moment that the serial history of the machine, which would later be called one of the best in its class, begins. Serial assembly began in these very months during the most difficult period for the country's entire industry. Factories worked to their limits, materials arrived with interruptions, and skilled labor was in short supply. Many specialists had been reassigned to other, more urgent sectors. Under such conditions, setting up the production of a new, structurally complex aircraft seemed almost impossible. And yet, the first machines rolled off the assembly line. The batches were small, not dozens, not hundreds, literally units at a time. Every assembled aircraft was the result of a separate small victory over component shortages, lack of parts, and constant supply disruptions. Engineers had to improvise literally on the go, replacing unavailable elements with accessible analogs, finding workaround technological solutions, and double-checking every component by hand where automated control was absent. It is worth understanding the scale of this problem. A modern factory today produces complex machinery along a strictly managed technological chain where every part arrives precisely on time and in the exact quantity. Here, the chain broke constantly. Sometimes a specific type of wire for electrical equipment was missing, sometimes a shipment of the required steel grade was delayed, or the only specialized machine tool in the entire workshop broke down. Yet despite all these difficulties, finished machines rose into the air. The first combat use of the new technology was, strangely enough, not offensive but reconnaissance in nature. Crews used the aircraft to gather information, flying over territories, photographing positions, and monitoring movements. Not the most spectacular task, but extremely important. Accurate intelligence data often determine the success or failure of entire ground operations. And here, the very quality that was built into the machine at the drawing board stage began to reveal itself. Pilots who flew the new aircraft for the first time noted a handling smoothness that was surprising for combat technology of that era. The machine obeyed the control column almost intuitively, without requiring the pilot to constantly fight the controls, as was often the case with other models of the period. Imagine the difference between a car that you struggled to keep on the road every second and a car that goes where you want without extra effort. This is roughly how pilots describe the difference between the new machine and the technology they were accustomed to. The second quality that immediately caught the attention of experienced crews was endurance on long flights. The twin-engine layout, planned by the designers at the concept stage, began to prove its value here in real conditions. The machine could remain in the air for hours, cover significant distances, and still retain a sufficient fuel reserve to return to base. Of course, the number of aircraft produced during that period was small, not the mass production that would allow one to speak of the machine as a key element of the air fleet. But it was not about quantity. It was about the quality these few machines demonstrated with every flight. Tupolev, receiving reports from aviation units, read in them exactly what he had anticipated when designing the aircraft under the cramped conditions of the Special Bureau. The machine worked. It lived up to expectations. Most importantly, it showed potential that went far beyond the modest reconnaissance role assigned to it at the beginning. Gradually, as combat experience accumulated, the command began to realize that this machine could be trusted with far more serious tasks than simple reconnaissance flights. At this point, the next stage of history begins: the transformation of a reconnaissance aircraft into a fully fledged combat instrument capable of striking where needed. The command of frontline units was not accustomed to trusting new equipment immediately. There were too many instances where promising designs on paper disappointed in real conditions. Therefore, the transition from reconnaissance tasks to full-scale strike operations occurred gradually, step by step, as evidence accumulated that the machine was truly up to the task. The first reports from the front were encouraging. Pilots praised the maneuverability, noted stability in flight even under difficult weather conditions, and remarked that the machine forgave minor piloting errors, a quality highly valued in combat conditions, perhaps even more than speed. But the designers understood that to realize its full potential, the machine had to be strengthened. The reconnaissance version carried minimal armament and equipment. The role of a medium bomber required more. Engineering groups, continuing their work behind the walls of the Special Design Bureau, began making changes directly during serial production, a practice quite unusual for those times. Typically, improvements were accumulated, tested separately, and then introduced into a new model. Here, time was so pressing that improvements were introduced literally in batches, from series to series. The bomb load was increased. Defensive armament was added for protection against enemy fighters. The power plant was refined to handle the increased weight without losing flight characteristics. What happened next was something that, according to memoirs of contemporaries, not even Tupolev himself fully expected. The upgraded machine did not just handle its new role, it began to exceed the indicators set in the original technical specifications. The speed remained at a level comparable to many fighters of that period, a rare characteristic for a bomber, which by definition carries a heavy load and should therefore be slower than light combat machines. Imagine a truck that, when fully loaded, manages to overtake passenger cars on the highway. This was roughly the situation with the new version of the machine compared to other bombers of the time. This gap between typical expectations of a bomber and the real flight qualities of the machine became its signature. Crews used to the fact that after dropping their bombs, a heavy machine became a vulnerable target on the return journey, suddenly received an aircraft capable of quickly leaving the danger zone. Frontline command quickly grasped this feature. The machine began to be deployed in operations where not only strike precision was required, but also the ability to quickly enter the target area and just as quickly leave it, a task that most heavy bombers handled far worse. Tactics of employment also gradually changed. While previously the machine was used primarily for solo reconnaissance flights, now it was increasingly operating as part of groups, delivering coordinated strikes on selected targets. This evolution, from a solo scout to an element of a group strike, took relatively little time but fundamentally changed how the command perceived the machine. It is also worth noting another point often overlooked in telling the story of this aircraft. Every refinement made by the engineers occurred under conditions far from ideal. The specialists working on these modifications were still in the Special Design Bureau, still worked under supervision, and were still limited in their access to resources. Yet under these very conditions, the machine continued to evolve, becoming an increasingly formidable instrument at the front. By the beginning of 1943, it was clear that the designers had created not just a successful aircraft, but a machine with a major reserve for further development. The only question was whether the project would receive the opportunity to fully realize this potential, or if it would remain restricted to small series produced under constant shortages. Tupolev decided to seek the answer to this question not at the factory or in the design bureau, but directly from the highest leadership of the country. January 1943. On the table in front of Tupolev lies a blank sheet of paper, not a blueprint, not a calculation, not technical documentation. A letter, addressed personally to the leader of the country. The decision to write such a letter was not an easy one. A man whose own status remained uncertain, whose name was still on the list of those convicted under a political article, took the initiative to appeal directly to the highest leadership with a request to continue work on the project. It is important to understand the context. At that time, a direct appeal to the head of state was an exceptional event, even for people with impeccable reputations. For a person in custody, such a step bordered on outright risk. The letter could simply be ignored, or it could be viewed as an act of excessive self-confidence. The reaction was unpredictable. And yet Tupolev decided to take the risk. The reason was simple yet compelling. He saw what his machine was achieving at the front and understood that without full support, this potential would remain unrealized. In the letter, the designer did not ask for leniency regarding his own fate. He spoke exclusively about business. He presented specific data from the front, how the machine performed in difficult combat operations, how pilots noted its reliability, and how it completed tasks that other models of the period failed to achieve. The argument was built on facts, not emotions. Tupolev listed specific episodes of combat use where the machine demonstrated exceptional qualities. He pointed to feedback from flight crews and emphasized that with further refinement, the aircraft could fill critical requirements of the Air Force in the medium combat aircraft class. Every word in this letter carried weight. The designer understood that the persuasiveness of his arguments mattered more now than ever. This was not just a progress report. It was an attempt to prove that the work he was doing was more important than the formalities of his own status. Imagine for a moment the position of this man. He was simultaneously the creator of one of the most promising combat machines of his time, and a person whose personal fate remained in limbo. The letter he sent could either open the path to the project's full implementation or receive no response at all. The risk was not only professional. Any direct appeal to the top in that system could be interpreted in various ways. But Tupolev gambled on the fact that the results of the work spoke louder than words, and the gamble paid off. An answer came, not instantly, but in a relatively short time by the standards of the era. The country's leadership decided to support the further development of the machine. This meant not just formal approval, but the allocation of additional resources, expansion of the design team's capabilities, and a new stage in the project's history. For Tupolev, this decision was confirmation of what he had believed since the beginning of his special confinement, that engineering talent and real results can break through even the most rigid bureaucratic and political barriers. It is difficult to overstate the importance of this moment for the subsequent history of the machine. Without this letter, without the designer's willingness to take a risk and appeal directly to the highest leadership, the project might well have remained at the stage of a modest reconnaissance model produced in small batches. Instead, the path was open to something much more massive. Within months of this letter, Tupolev's team would receive what they had waited for so long, a full production base to continue their work. It was there, at the new facility, that the version of the machine destined to go down in history as one of the best in its class would be born. April 1943. Tupolev's team is allocated plant number 156, a production facility of a much larger scale than what the team had worked with before. New workshops, new equipment, new opportunities. But one detail must be understood. This factory was still located on the territory of an institution with a special regime. The freedom of the specialist remained the same, that is, virtually non-existent. Only the scale of the tasks now facing them had changed. With the acquisition of the new plant, a phase began that is still debated among aviation history specialists. The question sounds deceptively simple. Was what they began creating at plant number 156 a deep modification of the existing machine, or was it actually a new aircraft built using previous developments? There is still no single answer to this question. To understand why this debate arose, one must look at the scale of the changes introduced by the design team. On one hand, the new version of the machine retained the basic layout, the twin-engine scheme, general fuselage proportions, and the basic principles established at the very beginning of the concept. From this perspective, it was indeed the development of an existing design, bringing it to refinement. On the other hand, the volume of changes was so significant that many components and systems had to be designed practically from scratch. The power plant was changed, internal equipment was redesigned, and the entire logic of weight distribution throughout the structure was revised. From this viewpoint, the engineers faced a task comparable in complexity to developing a new aircraft. Where exactly lies the boundary between a deep modification and a new design? This question is not as abstract as it might seem. On its answer depended how the project would be classified, what resources would be allocated to it, and ultimately how this machine would enter aviation history. Tupolev and his team viewed the situation pragmatically. They did not care much whether the result of their work was called a modification or a new project. It was important to solve a specific task, to create an aircraft that combined the best features shown by the previous version while eliminating the shortcomings identified during frontline operations. And shortcomings, despite all the successes, did exist. The machine remained heavier than the designers wished. Part of the equipment included in the original design turned out to be redundant for real combat tasks. A more powerful power plant was required to compensate for growing demands on speed and flight altitude. The engineers were presented with 4 primary tasks simultaneously, and each pulled the project in its own direction. The machine had to maintain its survivability, the ability to withstand damage and remain controllable. At the same time, it had to become faster to exit danger zones more effectively after completing a mission. It was also necessary to maintain and ideally increase flight range and to add versatility, the ability to use the same basic design for various tasks, from strike operations to reconnaissance and training young pilots. Combining all these requirements simultaneously was a task that looked nearly impossible on paper. But it was precisely for solving such problems that Tupolev's team had earned its reputation long before the designer ended up in the Special Bureau. The first major step toward a solution was working on the weight of the structure. Every extra kilogram meant a loss of speed, loss of maneuverability, and loss of precious meters of altitude. At the same time, every kilogram of armor meant an extra chance for the crew to return home after a combat mission. Finding a balance between these two extremes proved to be one of the most difficult challenges in the project's history. The engineers laid out the blueprint on the table and began calculating. Every joint, every component, every bolt, everything had its weight. And this total weight determined how quickly the machine could rise into the air, how high it could climb, and how much fuel would be needed to reach the target and return. The task of structural weight reduction sounds simple until you get into the details. In practice, it is one of the most thankless engineering tasks because every kilogram saved somewhere results in a loss elsewhere. The armored plating protecting the crew and vital components of the machine was one of the main reasons the previous version of the aircraft was respected by frontline pilots. This armor gave a chance to return home, where other machines became easy prey to ground and air opposition. Now the design team stood before a difficult choice. Remove some of the armor, and the machine would become lighter, faster, and more maneuverable. But it would also become more vulnerable, meaning the risk to the crew would increase. The engineers understood this better than anyone. Every decision to lighten a specific component meant not an abstract figure in technical specifications, but a real risk for real people who would fly this machine in combat. Instead of simply cutting away armor where it seemed convenient, the team chose a more complex but far more rational path. They began analyzing which areas of the aircraft were most frequently damaged in actual combat missions and concentrated protection there, removing excess weight from less vulnerable sections. This was painstaking, almost microscopic work. Reports from the front were studied, damage data from returned aircraft were analyzed, and statistics across different types of combat missions were compared. Based on this analysis, the designers redistributed the armor, not evenly across the entire structure, but selectively, where it truly mattered. In parallel, work was underway to optimize internal systems. Equipment that was duplicated in the original version, or turned out to be redundant in practice, was either removed entirely or replaced with lighter analogs without loss of functionality. Each such step yielded a gain of only a few kilograms, but these kilograms added up to dozens, and dozens into hundreds. With every saved kilogram, the machine became a little faster and a little more maneuverable. At the same time, the designers kept in mind the main goal of this work. The bomber had to retain the survivability that had already earned the respect of frontline crews. Not to turn into a fragile, vulnerable machine for the sake of a few extra knots of speed, but to find the sweet spot between protection and maneuverability. Alongside this, the team faced another task: versatility. The machine was being prepared not just for one specific role. It was assumed it could work as a strike bomber, as a reconnaissance aircraft capable of staying aloft for long periods, and even as a trainer for training young pilots just beginning to master combat technology. Combining the requirements of 3 different roles into one design was a task that would have defeated many design teams of the time. But Tupolev's team approached it methodically, step by step, finding compromises where compromise seemed impossible. By the end of this stage of work, the engineers had an updated design of the machine, lighter, more carefully planned in terms of protection distribution, and ready for the next critical test. But a lightened airframe is only half the equation. For the machine to demonstrate outstanding characteristics, another problem had to be solved, no less complex than working on weight: finding an engine capable of unlocking the full potential of the new design. And here, a major disappointment awaited the designers. On the first assembled prototypes of the new machine, they installed M82A engines, at that time some of the most powerful power plants available to Soviet industry. The logic was clear: a lightened, refined airframe plus a powerful engine should yield the exact result the design team was aiming for. The machine was taken into the air for its first control tests, and the result was discouraging. The State Commission receiving the new technology set clear requirements for the high-altitude characteristics of the machine. The aircraft had to reach a speed of at least 550 kilometers per hour at a certain altitude, a performance indicator that directly determined how effectively the machine could operate against anti-aircraft defenses and fighter aircraft. With the M82A engines, the maximum achieved speed was 545 kilometers per hour. A difference of 5 kilometers per hour seems like a trifle at first glance. In practice, this difference meant that the machine did not meet the Commission's requirements and could not be approved for full-scale serial production in its new configuration. Imagine an athlete who trained for months, gave their all at the competition, and missed the qualifying standard by a hair. This was roughly the position the design team found itself in after the first control flights. The engineers tried to refine the existing power plant to squeeze out extra power reserves. They adjusted settings, optimized fuel delivery systems, and looked for any opportunity to increase engine output without radical redesign. But the 545 km per hour ceiling remained an insurmountable barrier. Time was pressing. Every day of delay meant a delay in the upgraded machine reaching the front, where it was urgently needed. The team faced a serious dilemma: either accept the lacking characteristics and launch the machine in its current configuration, or look for a fundamentally different solution. The solution was found by an engine designer named Shvetsov, whose name would forever be linked with the history of this aircraft. Shvetsov proposed a bold step for the time, replacing the existing engine with the M82FN modification. The main difference of the new version was direct fuel injection, a technology that allowed the engine to develop significantly more power right from the start, without a long spool-up. The figures spoke for themselves. The new power plant allowed for a takeoff power of 1,850 horsepower, a figure that significantly exceeded the capabilities of the previous engine version. But any serious change to the power plant meant more than just swapping one unit for another. It meant revising the entire engine nacelle layout, redesigning cooling systems, and rechecking the aircraft's balance with the new engine characteristics. The team faced a massive task in extremely tight deadlines. The engineers understood that this was their last real chance to meet the Commission's requirements. If the new power plant failed to deliver the required result, the project risked stalling indefinitely, while the front continued to wait for a machine capable of filling the critical need for a reliable medium bomber. Work on integrating the new engine into the design proceeded almost around the clock. Every component of the engine compartment was recalculated. Every system was checked for compatibility with the increased power of the power plant. The moment arrived when the updated machine, equipped with M82 FN engines, was ready for a new round of testing. This time, the stakes were higher than ever. If Shvetsov's solution proved itself, the project would receive a massive push forward. If not, the team would have to look for other, far more radical ways to solve the problem. The test flight was scheduled for the summer of 1943. This flight would become one of the most significant moments in the entire history of the machine's creation. Summer 1943. A crew with serious experience was assembled at the airfield. People who were to take the updated machine into the air and find out if the decision to change the power plant had paid off. The crew was commanded by a pilot named Shelest. Before takeoff, standard system checks were performed. Engine started, instruments normal, communication working. But behind this routine procedure lay a tension felt by all the technical staff gathered at the edge of the field. The machine began its takeoff run. It lifted off the ground more confidently than the previous version with the less powerful engine. This was noticeable even visually by the angle of climb and rate of acceleration. In the cockpit, a focused silence was broken only by brief remarks. Altitude rising normally. Engine running smoothly. Continuing climb. Every minute of flight brought the crew closer to the control limit that determined the fate of the entire project. 550 kilometers per hour, the very indicator that could not be reached with the previous power plant. Now, this limit had to be either reached or the machine would once again hit its ceiling. The instrument needle continued to climb. 500, 520, 540. Technical staff on the ground monitored the telemetry, not taking their eyes off the readings. And then, the moment for which this entire test was prepared. The machine under Shelest's control reached a speed of 568 kilometers per hour. It did not just achieve the required indicator, it exceeded it with a serious margin. This was not simply a victory over its own previous limitations. It was superiority over one of the most formidable opponents in the air at that time. The achieved indicator officially exceeded the characteristics of the best fighter of the opposing side at that moment, the Bf-109F, a machine considered one of the most advanced combat units of its class. A bomber, a machine originally created to deliver strikes, not for aerial maneuvers at the limit of capabilities, managed to surpass a specialized fighter in the very characteristic where fighters traditionally excelled over all other types of combat aircraft. Imagine a typical delivery truck on the highway overtaking a race car built solely for speed. This is roughly how specialists of the time perceived the results of this test flight. For the design team, which had struggled for months with weight issues, the power plant, and the overall balance of the machine's characteristics, this moment was confirmation of the correctness of the chosen path. All the decisions made earlier, lightening the structure, targeted distribution of armor, and replacing the engine with a direct injection modification, came together in a single result that exceeded expectations. When the machine descended and landed, the atmosphere on the field was difficult to describe in words. Technical staff, engineers, and commission representatives all understood that they had witnessed a moment that would determine the project's fate for years to come. Soviet engineers had achieved a result where the new version of the bomber became a leader in its category. Most importantly, its speed and altitude characteristics were on par with fighter bombers, and in some parameters even exceeded them. But, surprisingly, the main achievement of this machine lay not only in record figures. The main thing was that the bomber was suited for real frontline conditions, the very conditions where there were no ideal airfields, polished logistics, or sterile laboratory parameters. This aircraft was not created for record tables. It was created to survive and perform tasks where conditions were far from perfect. In this, as subsequent history would show, lay its true strength. By the end of 1943, when testing was completed, it was clear that the new machine was significantly superior to the PE-2 model, which at the time was the main serial bomber of Soviet aviation. This superiority concerned not only speed or altitude characteristics, which we have already covered. It was about how versatile and powerful a combat instrument this machine had become. Let us take a single indicator for comparison: bomb load capacity. The PE-2 model could carry about 1 ton of ordnance. The new machine from Tupolev's team carried 3 times as much, about 3 tons. Imagine the difference between a person who can carry 1 backpack of gear and a person capable of carrying 3 such backpacks simultaneously without losing travel speed. This was roughly the difference between these 2 machines in real combat conditions. At the same time, the increased payload was not the only advantage of the new machine. The armament installed on it included 2 Shvak system aircraft autocannons and 3 UBT system machine guns designed for defense by the navigator and radio operator. This defensive arsenal was entirely sufficient to fend off 1 or 2 enemy fighters, providing precious time for the escort group to arrive. But if all these figures, speed, payload, armament, impressed specialists, the main feature of the machine, the very trait that literally saved crews' lives, was its survivability. Let us explain in simple terms what this means. The machine had 2 engines. The designers built a fundamental decision into the project. Even with a complete failure of 1 engine, the aircraft was not to lose control. This sounds like a technical detail. In practice, it meant the difference between life and death for specific people in specific combat missions. Let us take the PE-2 model for comparison. On that machine, even a minor malfunction of 1 engine often meant the virtually certain loss of the aircraft. The crew lost control, the machine lost altitude, and the chances of successfully completing the flight dropped sharply. With the new machine from Tupolev's team, the situation was fundamentally different. The controls allowed the crew to limp the damaged aircraft back to their airfield, relying on only 1 functioning engine. What was considered an almost inevitable disaster on other models became a manageable, though difficult, situation here. Exactly how many pilots were saved thanks to this design feature is impossible to calculate, but frontline reports of that period contain many episodes where crews that sustained serious damage to the power plant during a combat mission still managed to return to their airfield, where on other machines such an outcome would have been considered a rare exception, bordering on a miracle. Practicality immediately after the start of serial assembly of the updated machine was demonstrated in combat operations in 1944 in the Königsberg area. Heavy, high-explosive bombs of the FAB-1000 series, capable of destroying fortified concrete structures, as well as cluster munitions of the ABK-P-500 series, effective against widespread area targets in urban settings, were suspended from these aircraft. Neither domestic bombers nor machines of the allies of the anti-Hitler coalition could compare with the capabilities of this machine in such operations. This became clear almost as soon as it began to be used on this front. By the final stage of the conflict, the machine had turned into a true symbol of how engineering skill can turn the tide even where the opponent initially possessed technical superiority. In the spring of 1945, when the vast majority of combat operations were conducted using this machine, it was clear that this was not just a successful project, but one of the best combat aircraft of its time, proving its worth with every completed combat mission. It remained only to understand what happened to the people who created this machine, and what legacy their labor left after the conflict ended. Spring 1945. Rows of machines stood on the airfields, having become by this time the true workhorse of the medium aviation tier. Machines that only a few years ago existed only as blueprints laid out on a table under supervision behind a locked door. By this time, virtually all combat operations requiring a medium bomber were conducted using this machine. The reason was simple and eloquent. Armament was used that had been repeatedly tested in real conditions and had proven its effectiveness better than any theoretical calculations on paper. The journey from the first modest batches of late 1941 to this moment took just over 3 years. During this time, the machine went from a reconnaissance apparatus with minimal armament to a fully fledged combat instrument capable of carrying 3 times the bomb load of the main serial bomber of the previous generation, while retaining controllability even with serious damage. But the history of this aircraft is not only a story of metal, drawings, and technical characteristics. It is, above all, a story of the people who created it. The specialists of the Special Design Bureau, who worked under constant supervision and were deprived of basic freedom of movement, nevertheless created a machine that frontline pilots valued above many other models of that period. They did not do this because circumstances were favorable to them. Circumstances, to put it mildly, were the opposite. They did it because they were truly dedicated to their work. After the end of the large-scale conflict, the engineers finally received the opportunity to work in normal conditions, without the constant control and restrictions characteristic of the Special Design Bureau. Many of the specialists who spent years at the drafting table under supervision returned to full professional activity, continuing to develop the industry in which they had shown themselves so brightly during the most difficult years. The experience and developments gained during the creation of this machine proved to be by no means a temporary episode that could be left behind. The solutions found by Tupolev's team, the principle of distributed armor, the approach to the balance between weight and protection, and the philosophy of structural versatility, laid the foundation for many subsequent developments of the Soviet aviation industry. Today, when many archival materials of that period are declassified and available for study, aviation history specialists are often surprised by one simple fact. How could a machine of this class, with such outstanding characteristics, be designed under the conditions of a special design bureau, under supervision, with limited access to resources, by people whose own status remained uncertain? The answer to this question, when analyzed, turns out to be remarkably simple. Talented engineers remain talented engineers regardless of the circumstances in which they have to work. Their knowledge, their experience, and their ability to find unconventional solutions to complex technical problems do not disappear because circumstances turn out to be unfair. These people continued to do their job as best as they could, because they believed in the importance of what they were doing and wanted to serve their country during a difficult period. The history of this aircraft is a story of how professionalism and dedication to a cause can pave a way through even the most difficult life circumstances. A story of a machine that was born in conditions poorly suited for design work, and yet became one of the best in its class. Today, looking back at this history decades later, we see more than just technical characteristics and combat indicators. We see confirmation of a simple truth. The mastery finds a way to show itself, even when conditions are set against it in the most severe way. Perhaps this is the main lesson of the history of the machine born behind a locked door.